Alright, this is NCCER Electrical 4, Revision 10, Medium Voltage Terminations and Splices, Chapter, Module number 26411-20. Get right into it. Medium voltage splicing. Trade terms in this chapter. You're going to need, like some cables have armor, and you're going to need to know how to cut through that and get into that to prepare for a splice. Shielding, we've talked about before what a shield is, shielding braid, what a splice is. You should know what a splice is by now. Stranded shielding, you have a couple different types of shielding. And then stress, the stress that's put on a splice, and there's things to alleviate that stress. My first highlight is the first sentence on the page. Medium voltage cable covered in NEC Article 311 is defined as a single or multi-conductor solid electric insulated cable rated at 2001 volts all the way up to 35,000 volts. So the NEC is saying the medium voltage cable is between 2 and 35,000 volts. 111 medium voltage cable configuration components. So they can have different types of wire inside of a cable. You can have concentric stranding, compressed stranding, compact stranding, solid wire. I have the third bullet point, the compact stranding, highlighted. Compacted to 90% of the concentric conductor diameters. Although this conductor has full ampacity ratings, the general rule for sizing is to consider one of the conductor size smaller than the concentric or compressed cable. This reduced conductor size results in a proportional reduction of all cable layers, a consideration when sizing for molded rubber devices. So that just compacts everything and makes the cable even smaller than either the compressed or the concentric stranding. At the bottom of the page, that last section, I've got the first sentence highlighted. Despite their differences, all medium voltage power cables are essentially the same, consisting of the following. They got all the bullet points going through the different parts. I have the insulation shielding system highlighted. You need to know that that's either going to be semiconductive or metallic, or semiconductive and metallic. Going on to page 2, strand shielding. So for my instrumentation students, this shielding is not exactly like instrumentation shielding. This doesn't have signals in it. This is like power wire shielding. So not quite the exact same. But yeah, the strand shielding 111. I've got the whole first 2 paragraphs highlighted. 3 sentences. Strand shielding is the semiconductive layer between the conductor and insulation that compensates for air voids between the material. Air is a poor insulator. Key in on that. Having a nominal dielectric strength of only 76 volts per mil, whereas most cable insulations have dielectric strengths over 700 volts per mil. Without strand shielding, an electrical potential exists that will overstress the air voids. Still 2 more highlights in this same section. First sentence is one of them. As air breaks down or ionizes, it produces a corona discharge or corona discharges. Skip a sentence and the rest of that section is a separate highlight. The semiconductive strand shielding eliminates this potential by simply shorting out the air. Modern cables are generally constructed with an extruded strand shield. Strand shielding is shown in figure 4. So you can see that over on page 3 on the bottom. You can see those that strand shielding. Let's see if I've got strand shielding in this picture right here. It shows the shielding that's below that, and then if there's actual air in here, they can have corona discharges, but that strand shielding eliminates that, the potential for that. Insulation 112. You're gonna test stuff at different or test insulation at different levels in the factory. So they got the 100% level, 133%, and the 173% level. I've got the 173% level in 112 highlighted. 173%. Cables in this category should be applied on systems where the time required to de-energize a grounded section is indefinite. Their use is also recommended for resonant rounded systems. Consult the manufacturer for installation thickness requirement. So those are tested up to 175%. Moving on to page 4, the jacket of the cable. Just a little short section there. Second to last sentence is highlighted in 114. Typical materials used for cable jackets are PVC, neoprene, and lead. PVC, neoprene, and lead used for cable jackets. 120, making straight splices. So like an end-to-end splice. Going to have several highlights in this section. 120, going on the right-hand side of the page, the second to last paragraph, last sentence is highlighted. The slightest amount of moisture, dirt, or foreign material can render the splice useless. If you have dirt or moisture or anything in the splice, you're creating a failure point in that splice, so you want to make sure that a splice is free of those three things. Page 5, first paragraph, second sentence is highlighted. In general, the conductor jacket and insulation should be removed for 1/2 of the conductor length plus 1/4 inch. So 1/2 of the conductor length plus 1/4 inch. Sorry, not conductor. Connector length. 1/2 of the connector length plus 1/4 inch. Right hand side of page 5, the paragraph that's right above the bullet points on the right hand side, right above 121, that paragraph is highlighted. To finish off the splice and ensure complete protection over the entire splice, cover the entire splice with 4 layers of vinyl electrical tape, extending about 1/2 inches beyond the edge of the splicing compound. 4 layers of tape to finish off the splice. Right after that, the next part is highlighted. The 5 basic tasks in building the splices are. You got those 5 bullet points. I've got the last one highlighted, rejacketing, and then out to the side of that I wrote typically your final step. So your final step of building a splice is rejacketing, typically. Preparing the surface. So in preparing for a splice, going on to page 6, using abrasives. I've got the first sentence of abrasives highlighted. Research has proven that 120 grit abrasive cloth is fine enough to protect the medium voltage interface and yet coarse enough to remove silicon residue without loading up the abrasive cloth, which means that it's getting into the abrasive cloth. So you're using 120 grit abrasive cloth on these medium voltage splices. Moving on to 122. Joining the conductors with connectors. Page 7, I've got the third full sentence on page 7, or second to last sentence of that started paragraph highlighted. The suitable connector for medium voltage cable splices is a compression type or crimp type. So you're not using the split bolts. Do not use split bolts for this. Can you use that connector? No. The immediate next paragraph, the whole thing, next paragraph, skip a sentence and the rest of the paragraph is highlighted. Aluminum conductor should be connected with an aluminum body connector preloaded with contact aid, so that antioxidant paste to break down the insulating aluminum oxide coating on both the connector and the conductor surfaces. That makes aluminum corrodes or oxidizes, so you want to put that paste on there to make sure it doesn't oxidize. Oxidation can act as an insulator. You don't want an insulator in your splice where you don't want it. They talk about re-insulating and using tape, heat shrink tubing, molded rubber splices. I posted a link to a video on them doing a full-length splice. I recommend you go watch that. That's in the that should be right below this. The practice test for this, the video for that. Pages 8 and 9, reshielding and rejacketing. I don't have anything highlighted in those, but they just go through those are the last 2 steps for making a splice. Making inline tape splices, 130. They go through the steps on making inline tape splices. As you can see on pages, I don't have anything else, I don't have anything highlighted in 8 and 9 or 10 and 11 where they start going through the steps, preparing the cable, how far to cut back, going on to page 12 and 13. I do have step 8 highlighted. Penciled insulation at each end using a penciling tool or a sharp knife for a distance equal to B in figure 10. Buff the tapers with an abrasive cloth so that no voids will remain after the joint is insulated. So if you go back and look at figure 10, or what's up, the same one that's on the board, this one that's on the board, you can see that you are going to pencil for just this distance right here, and then buff the taper of that with an abrasive cloth. Applying primary insulation. That starts on page 12, and on page 13 I've got the first couple sentences of that note highlighted. To eliminate voids in critical areas, highly elongate the splicing tape in the connector area and the splice ends near the cable semiconductor material. Stretch the tape just short of its breaking point. This electrical tape has a lot of elasticity, and the further you stretch it out, the tighter it's gonna wrap up on this stuff. So you're pulling this stuff as tight as you can when you're making these splices, almost to the point of breaking. Going on to page 14. They go through, starting in 140, manufactured termination splice kits. So most of the stuff they sell as a splice kit with 3 different splices. Very expensive, a few $100 each usually. Heat shrink kits. So you can buy a heat shrink kit, 141. The whole first paragraph in 141 is highlighted. Heat shrink splice kits have large use ranges and allow the connection of different conductor sizes. So you can connect different conductor sizes with these heat shrink kits. Different insulation types, for example, paper insulation to polymeric insulation, and different cable constructions. For example, 3 conductor cable spliced to single conductor cable. Do a lot of things with these heat shrink kits. They go through the steps on how to use the heat shrink kit. On page 16, they go through cold shrink kits, 142. You can read through on how to use the cold shrink kits, but I do have step 1 in 142 highlighted. Step 1 is clean each cable jacket by wiping with a dry cloth about 2 inches from the end. So your first step is going to be cleaning just making sure that there's no debris. Like I said before, you don't want debris or foreign material in any of these splices. They continue on through the on how to do that, like preparation, how to splice. Continuing on, I don't have any highlights to the end of this section, which is on page 23. You've got 4 questions for section 1. It's by far going to be the most used section in this chapter. But I'm going to continue on to section 2. Section 2 is going to be terminating medium voltage cable. You're going to have different classes for terminations. Page 24, termination classes. The whole, all the way from 210 all the way through that 3rd bullet point is highlighted. A class 1 cable termination, or more simply, a class 1 termination provides the following. Some form of electric stress control for the cable insulation, shield mount, terminus, complete external linkage insulation between the conductor and ground, and then key in on this last point. You have to have a seal to prevent the entrance of external environment into the cable and to maintain the pressure, if any, within the cable system. That class 1 termination is the only one that's going to be able to seal against external environment stuff. On the right hand side of page 24, I've got the first sentence of the class 3, or the 2nd bullet point on the right hand side of 24 highlighted. First sentence. A class 3 termination is the one that provides only some form of electric stress control for the cable insulation shield terminus. grounding. I don't have anything in grounding the shield's ends, but for my instrumentation students, this is where it's different. First sentence of 212 says that all shields are normally grounded. However, individual circumstances may exist where the shield ground is only at one end. It's called floating one end, like we do instrumentation. These are power cables. They are not signals. They're not sending signals across these cables. So they are not the same as an instrumentation cable for all y'all out there. They're different. So most of the time you are grounding the shields on both ends. The next highlight that I have is 213, external leakage insulation. First sentence is highlighted. Insulation must provide for two functions: protection from flashover damage and protection from tracking damage. Down at the bottom, you'll have your BIL ratings, insulation class, and BIL, which is the basic lighting impulse insulation levels. You're going to have a question come out of Table 1. So just make sure you highlight Table 1, and you'll have a question or review coming out of that. It's page 26, 220. Stress control methods. So stress is like if a wire's hanging in the air and the stress that's put on the wire. The last part of 220, right before 221 on the right hand side of page 26, that last couple sentences with the two bullet points is highlighted. All terminations must provide stress control. This stress control may be accomplished by two commonly used methods. You can have geometric stress control and capacitive stress control. They go through 221, just talks a little bit about geometric stress control, nothing highlighting that. Going on to 222. Capacitive stress control, first sentence is highlighted. This method consists of material possessing a high dielectric constant, generally around K30, and also a high dielectric strength. So that's, remember, a capacitor is just two plates separated by a dielectric, so that's the dielectric constant that they're giving. So generally it's in that K30 range. You got two questions for section 2 on page 28. I'm going to continue on to section 3. Section 3 is going to be on your high pot testing. So this is like a larger version or more in-depth version of measuring in a way. You're just testing things at longer and higher voltages. They talk about testing versus DC versus AC and which one you should use. Most of the time these tests are done with DC testing, but just this sentence that's in the on the board at the bottom is the one I have highlighted all the way in the bottom left of the page 29. Although DC testing may not simulate the operating conditions as closely as AC testing, the many other advantages of using DC make it worthwhile. So DC is mostly used, but you need to know that AC testing resembles the operating characteristics most closely. So using AC is the closest to testing stuff in the normal operation. Moving on to page 30. Types of high pot tests 310. First sentence is highlighted. DC high pot tests are performed primarily to determine the condition of the insulation. Alright, so you pretty much for a high pot test, you can see up here on the board, you increase voltage to see what the current does. And whenever the current starts to spike, that's where your insulation is breaking down. So they test at A, increase voltage, let it sit at B, still good there, steadily going up, still good at C. As soon as it starts to turn up, this is called the knee right here. This is where the insulation is starting to break down, so they can test or say this cable is good for up to wherever they determine the cutoff is well before the knee. My highlight for this splits the pages. So it starts on page 30 in the bottom right of page 30. Right there where you see point C in parentheses, about 6 lines up through point D on page 31. At some point the current will start rising at a more rapid rate. That's called the knee, point C. This will show up on the plot as a knee in the curve. It is very important that the voltage increments shall be small enough so that the starting point of the knee can be noted. If the test is carried beyond the start of the knee, the current will increase by a much more rapid rate. The breakdown will soon occur. So that breakdown is happening between C and D where the knee is on that graph. That's your breakdown insulation. They go through and talk more about that and how they're doing these tests and stuff. I don't have any highlights in 32 and 33. 320 goes into making connections and making your connections, doing a high pot test. Sorry. But if you go on to page 34, they go through the steps of this. I have step 7 highlighted. So step 7 is plug the line cord into 120 volt 60 hertz single phase outlet and clip the ground wire coming from the line cord to the conduit receptacle mounting screw or another ground source. So all you want to get out of that is for your high pot test, your high pot is using a 120 volt source. You're also going to need a voltage regulator, so your regulator that moves your voltage, like your tens of thousands of volts higher and higher. On page 35, that last full paragraph right before that little bit of math right there, the whole thing's highlighted. The use of a line voltage regulator under such conditions greatly increases the usefulness and ease of operation of the equipment. In general, the power rating of the regulator should be based on the maximum power output capability of the tester multiplied by a factor of about 1.3. For example, a tester rated at 75,000 volts at 2.5 milliamps can deliver the following output power. 75,000 volts times 2.5 millivolts is 187.5 watts. And then 187.5 watts times 1.3 is 243.75 watts. So that's where it's saying that like the power factor should be about 1.3 is what you want to know. Moving on to page 36 and 37. I don't have any highlights on these pages. You can read through here and look up the like selective guard service connections. These are just different guards that are put in place. Moving on to page 38 and 39. 330 detailed operating procedure. I've got step 3 highlighted on page 39. Highlighting that first sentence and determine the maximum test voltage to use, and then going along with that, skip the next sentence, and I got 2 more highlights in this step 3. As a rough rule of thumb, proof testing is usually conducted at 60% of the factory test voltage. The next sentence is separate highlight. Acceptance testing would call for a maximum value of about 80% of the factory test voltage. So that's for acceptance testing. Proofing is 60%, acceptance testing is 80%. They go through the steps, they continue on doing the steps of that all the way through page 41. A much simpler test is the go, no-go testing in 331. In 331, the second paragraph is highlighted. A much shorter and simpler test may be sufficient in those cases where the contractor, purchaser, or operator is only interested in knowing whether or not the insulation meets a specific high voltage breakdown requirement. That is, whether the equipment or cable would withstand X kilovolts without breakdown. That is a go, no-go test. So much simpler test. That is all my highlights for this chapter. You got section 3 review on page 43. You got 10 questions on 44 and your supplemental exercise on 45, and then along with the practice test that you'll have on campus.